Okay, so hi everyone, and welcome to this sixth lecture on the series on the massive binaries. So today we have the pleasure of having Kunal Deshmukh, who's going to talk about high mass X-ray binaries and pulsars in binary systems. But before he moves on to his presentation, let me introduce him a little bit. So he is currently a third year PhD student in the Institute of Astronomy at KU Leuven in Belgium. He did his master at Texas Tech University. The topic of his PhD is the multiplicity of evil massive stars, and he planned to graduate in summer 2027. And here I would like to take the opportunity to advertise his paper that is titled Investigating 39 Galactic Wolf-Rayet Stars with Gravity to Uncover a Long Period Binary Desert, which basically they found that there is a lack of wide Wolf-Rayet plus OB type stars binaries. So with that, if you're ready, Kunal, then the floor is yours.
Yes. Thanks for the nice introduction. Can you hear me okay? Yes. Uh, so yes, in this sixth lecture, I want to today talk about high mass X-ray binaries and pulsars in binary systems, which is a topic that doesn't very often come up in our typical massive star conferences. So it was very interesting to go into the details of what goes on in these very nice systems. So I would very briefly like to start with a bit of history. So X-ray astronomy, unlike optical astronomy, is a very young field. The first X-rays from a source other than the sun were only discovered in 1962. So on the left here we see a plot, sorry, a picture of this quote unquote telescope. So it's not exactly a telescope; it's more of a detector, which was shot up on a rocket above the Earth's atmosphere to see if we can detect X-rays from extrasolar sources. And that is how the first X-rays were discovered. Over the years, these detectors got more and more sophisticated. So on the right, there is another quote unquote telescope. So not your typical telescope, but with some collimators on it, which was called the Uhuru, which was able to find many more sources in the sky. If we fast forward to today, the X-ray view is much more sophisticated. So this is a nice image from the E Rosetta X-ray telescope. This is in the zero point 0.3 to 2.3 keV energy range. And what we see here is millions of X-ray sources in the sky. So that is how advanced we are in our sensitivity of detecting X-rays from not just galactic but also extragalactic sources. But coming back to how things started, after these first few X-ray sources were discovered, it took quite some time to actually localize them. So basically, if you can tell the X-rays are coming from a certain part of the sky, you still need to know which exact star are they coming from. So to go from the part of the sky to the exact star took some time and effort. But what they found was a lot of these sources were actually binaries, and that is where the term X-ray binaries comes from. Uh, and as you would expect, some of them, the low mass X-ray binary was found to have binaries where one of the star we see in the optical was a low mass star, and then for the high mass stars we call them high mass X-ray binaries. So in this talk, I'll focus on high mass X-ray binaries, but I would say low mass X-ray binaries are equally fascinating. In both cases, though, one thing that is common is the source of X-ray emission is accretion of material onto a compact object. So this immense amount of energy is being released only because we are dumping material on a very compact object like a neutron star or a black hole. So that is something that will show up in most X-ray binaries that we know. So I have an example on the right here. It's an artistic impression, of course, of Cygnus X1. This was the first confirmed stellar black hole, which you might know from a famous debate between Kip Thorne and Stephen Hawking, who were debating whether or not it's a black hole. So now we are very sure it is a black hole, but this is how far we have come in about 50 years. In context of massive binaries, if we look at this plot, which we have seen quite a few times already, if we start with main sequence stars, we know that in the massive regime, you can go through mass transfer where you can form a step star that can collapse into a black hole. You can also go through further interaction to form a second black hole, and then you have merging black holes. So this is one popular channel of forming merging black holes. And high mass X-ray binaries can be an intermediate step going from massive main sequence binaries to merging black holes. So they are very intriguing objects if we think about them in this context of this chart of massive binary evolution. Um, there are many further subclassifications in high mass X-ray binaries. I will discuss three main ones in here, but that is not to say these are the only ones. So depending on what the other companion is, so we have one companion that is one star that is a compact object, either a neutron star or a black hole, and the other star, uh, which is still uh, a normal, so to say, star, can also decide how this X-ray binary looks. So some types are basically a BE X-ray binary if this other star is a BE star. This would not be surprising because if you look at the mass transfer phase, that can easily spin up the companion, which can then start looking like a BE star. Um, but not always the case. So sometimes you can also have supergiants that are companions, and supergiants can have very strong winds, which can feed material onto the compact companion. So these are called wind-fed high mass X-ray binaries because the wind is feeding the X-ray binaries. And the third one I would like to mention are the Roslow filling ones, where if you have these two stars quite close together, uh, the the companion or the donor can start filling its row slope and then very efficiently accrete material onto the compact object. This also leads to the formation of often the formation of an accretion disk. So these are termed as disk-fed high mass X-ray binaries. Some visualization for these. So we have some example pictures. All of them are artistic because, or either simulations or artistic because we can't really uh, see these stars or resolve them very nicely. But on the top left, we have the disk accretion case where you can see formation of a nice accretion disk around the compact object. The bottom example is a BE binary, BE X-ray binary, where the BE star itself has a very big decretion disk. And the third example on the right is a wind-fed system, which is a famous Vela X1 X-ray binary system that has been extensively studied. So to look at high mass X-ray binaries, there are many different ways, but in this talk, I'll focus on two perspectives, one from the donor very briefly, and then one of the accretor, so where I'll discuss a bit more about how the nature of the compact object can dictate what we see. So the first one is from the perspective of the donor, and I'll just go over the three cases that I just mentioned. The first case was that of a BE star. So uh, this plot shows a typical BE star in a binary with a compact object, and what you see here is first of all the orbit, which is quite elliptical. Then you have the BE star, which has a very big accretion disk. I mean, this is not exactly to scale, but the decretion disk is usually quite big. Um, so whenever the compact companion passes through this decretion disk, it has the opportunity to basically accrete material. So what is very typical in this kind of a system is that since this motion is periodic at the period of the orbital period, you can see periodic X-ray bursts coming from such X-ray binaries. Another common feature is that they tend to be eccentric, at least many of the ones that we know are eccentric. This is kind of intuitive because when these compact objects form, they might receive a kick, and this might introduce eccentricity even if those systems were not eccentric before. But this really helps with this periodic outbursting because as soon as your new compact object goes out of the decretion disk, the X-ray emission can go down and then it can go up again when it passes through the disk. Um, then we have the supergiants. So in the wind-fed scenario, what we really need to understand is the accretion heavily depends on how the supergiant is shedding its mass, right? How it's losing its mass. And what we have heard a bit in the in the winds lecture series as well, is that winds are not something easy. You can't have a constant mass loss rate that is nicely accreting onto the compact object at a constant velocity or density. So we can see that using this nice plot here, which is actually a snapshot at a fixed time, showing two things. In the top panel, we see the density, and in the bottom panel, we see the velocity of the wind as a function of distance. And we see it's not even close to being uniform. There's a lot of variability in there. And this often shows up as variability in the X-rays because this is the matter that is falling onto the compact object. So if matter falling is variable, then the emission from the compact object can also be variable at such time scales. Another thing that is worth noting is that accreting via winds is not the most efficient way. I mean, it's if the two stars are close, of course, it is efficient enough for us to see them as X-ray binaries. But what is even more efficient is the next case, which is the Roslow overflow, where if your donor is filling its Roslow, it can nicely funnel mass through this L1 Lagrangian point and form an accretion disk around the compact object. So this is much more efficient transfer of mass, and which results in much more efficient X-ray luminosities. Uh, Very briefly, I want to mention here also something that is kind of intermediate, where if the star is not fully filling its Roslow, but it's close to filling its Roslow, the winds of the star can still fill the Roslow. And this is something that is termed as wind Roslow overflow. So this is a bit more efficient than your normal winds, but a bit less efficient than your full Roslow overflow. Okay, so I will now switch to the accretor. And in most of the X-ray high mass X-ray binaries we know, uh, most of them have actually neutron star accretors. This has some support from the fact that there are more lower mass stars than higher mass stars, uh, and there are also many other factors involved. But given that most high mass X-ray binaries we know have neutron stars, I'll spend more time on neutron stars. So, if you want to accrete mass onto a neutron star and determine how much X-rays is it going to emit, a very first order approximation we can make is well, the X-ray luminosity. If we assume the X-ray luminosity comes exclusively from the energy released by the capture of new material. So, if you have new material from the winds of the companion and you accrete it onto the neutron star, the potential energy that it's losing is given by this equation G mc dot over RC, where mc and RC are the mass and radius of the compact object, in this case a neutron star, and m dot is the rate of accretion. Um, so this seems simple, right? If you assume everything is spherically symmetric, the m dot is coming in nicely from the donor, and you get this. If we go one layer deeper, we see that okay, but this m dot has to depend on some other factors, right? It has to depend on the mass of the neutron star that is accreting, because the more massive it is, the more efficiently it can accrete. It has to depend on the density and velocity of the wind, or the mass coming from the donor, which are rho and v in this case. And then for the velocity, we have the beta law, which is again a first order approximation that gives us some idea of what is the velocity of the winds. And then we can go further and further. And the point of this slide is not to discuss every parameter here, but the fact that there are so many parameters. So in the end, there's this uh, crude equation assuming this scenario where the X-ray luminosity is sensitive to the mass of the compact object, the mass of the donor, the separation, the terminal wind velocity, and so on. So it's a very complicated process. Uh, and in fact, this is still the simpler version because we are going to make it even more complicated by adding the fact that neutron stars are highly magnetic. So because you have, and by highly magnetic, I mean like seriously magnetic, trillions of more times than what we have on the Earth. And these magnetic fields will also interfere or contribute to how mass is being accreted. onto it, right? So we have to take this into account basically whenever we want to understand how mass is being accreted and how we get this X-ray luminosity from such systems. One thing I'll quickly note here is the fact that the rotation axis of the neutron star and the magnetic axis don't have to be aligned, and in most cases they are not aligned. At least the ones we see. This could be an observational bias because the ones we see are also the ones uh, that are not aligned. Because to see the pulses, we need them to not be aligned. Um, but this adds another layer of complexity to the accretion problem. So to understand this a bit better, uh, briefly describe some of the characteristic radii involved in the scenario. So for the new, so on the right, there is a cartoon of a neutron star with its magnetic field lines, um, and it can have different characteristic radii. So first of all, we have RL, this is the light cylinder radius. This is the radius around the neutron star at which the magnetic field lines start rotating at the speed of light. So beyond this, you start getting electromagnetic radiation from the neutron star, and this becomes very relevant in single neutron stars that we see as radio pulsars and so on. Uh, in our case, however, every all other radii are within this radius, so we don't have to worry about the light cylinder radius as such. Then we have the magnetospheric radius, RA, also called the Leuven radius. This is a radius beyond which this is a radius at which the magnetic pressure outward and the ram pressure or the pressure of the incoming material inward is balanced. So this is where the magnetosphere is kind of holding the material. Then we have the co-rotation radius. This is the radius at which if you are co-rotating with the neutron star with the same angular velocity, you're also at Keplerian velocity. So anything beyond that uh, is super Keplerian in some sense. Then we have the gravitational capture radius. So this is a bigger radius where material is bound to the neutron star. So if something is within this radius, we can say it is bound to the neutron star. Even if it's not accreted onto it, it's still bound to the neutron star. And finally, we have the stopping radius r stop. So this is, I mean, this doesn't have like a single value. This depends on the different parameters that are in play, and this basically tells us where is the material stopping, until where can the material get until it faces an equal and opposite push out. So with all these in mind, I want to discuss a few cases of accretion onto the neutron star. The first case is when the magnetospheric radius is bigger than the co-rotation radius. So what happens in this case is that, as I said, if you're beyond the co-rotation radius and if you start co-rotating with a neutron star, you're at a super Keplerian velocity. So uh, the matter that is at this radius and trying to co-rotate will be flung away, uh, and it can't accrete anymore. So what we get is a centrifugal barrier. So material can't really penetrate through this if we are in this regime. Uh, but since the matter is still within the gravitational radius, so you can see Rg is greater than Ra. This means that there is between Ra and Rg, the material can still hang around, right? And what it does is forms a nice quasi-static envelope. This is a convective envelope because matter is constantly being flung away from this boundary, so you get convection happening in there. In such a case, accretion is minimal, but you do get a drag on the magnetosphere, right? Because it's trying to drag away this material that is at the magnetospheric radius. So you lead to spinning down the neutron star a bit because it's losing a bit of angular momentum. The second case is what if the co-rotation radius then is higher than the magnetospheric radius. So in this case, matter doesn't have to be flung away because it is sub-Keplerian, so it can still co-rotate nicely. But in this case, what we have is the magnetic field itself creates a barrier. So in this case, we have a magnetic barrier uh, which doesn't allow matter to penetrate. It does still allow matter to go along the magnetic field lines, so you get some accretion. It's not super efficient, but it's enough. It's at least slightly more than the previous case. The quasi-static envelope that has been formed is still around, so that is still there. But if we go one step further and let this envelope cool, this basically opens the door for the onset of Rayleigh-Taylor instability, which basically means matter can seep through this magnetosphere much more efficiently, and we can start seeing a much more efficient accretion onto the neutron star, again along the magnetic lines. Uh, Now, if you remember that uh, the the rotation axis and the magnetic axis are not aligned, you can probably guess that with such accretion, you can very easily contribute to the angular momentum of the neutron star and spin it up again. Um, so this will basically be a state where we are accreting efficiently, but we are also spinning up the neutron star. So this is neutron stars are not necessarily always in one or the other state. They can change back and forth, and it really affects whether or not we can detect such systems. Because, for example, if you're accreting very efficiently onto the neutron star, it means it can emit more X-rays, and if it can emit more, we can see them. So just because we see a lot of the cases on the right does not mean there are not cases on the left, because they are harder to see. So there are some observational biases involved that we need to understand. But given this process where it's a bit of back and forth, where increasing accretion spins it up and then spinning it up can basically inhibit accretion and then so on, you can get a quasi-equilibrium. And there is a nice way to look at how this quasi-equilibrium sits in this nice plot. So on the x-axis here we see the orbital period, and on the y-axis we have the spin period, and we have different types of um, high mass X-ray binaries with neutron star companions sitting in on this plot. So if you look at, for example, the bottom left, which are the disk-fed binaries. For the orbital period, you would imagine these have to be very short, because if they are disk-fed, they are Roslow filling, they have to be at very small separations. So that makes sense. But also in the spin period, because they are creating matter very efficiently onto the neutron star, it's very easy to spin it up. So the spin periods are very small. If we look at supergiant binaries instead, these can be a bit wider, but not too wide. So the periods are of the order of 10 days, but the spin periods are a bit longer, because it's not that easy to spin up the neutron stars in such cases. And then we also have a bunch of B X-ray binaries, both in the Milky Way and the Magellanic Clouds. Those can have much longer periods, because if the orbits are eccentric, as long as the neutron star passes through the decretion disk at some point, we are going to see them as X-ray binaries. So those can be at much longer periods, and also the spin up is also kind of correlated to the orbital period. Uh, so yes. So if we want to look at how all of this works out in a nice animation, uh, this is this is a picture that shows a bit of what I've talked about. So you see this nice convective envelope around the neutron star. The neutron star is in the center, of course. You have accretion happening through the poles, and then you have this nice cone that is basically your X-ray emission. I would like to point out that none of this is to scale. The neutron star is of the order of 10 kilometers in size, so this is not to scale, but it's a nice animation to see how pulsars show up, right? Because if you have such a neutron star that is spinning, uh, and the magnetic axis and the rotation axis are not aligned, we see this like a lighthouse beaming, and whenever this points at us, we see an X-ray pulse. So this is how X-ray pulsars show up for us. This also shows we can easily miss such systems if this lighthouse beam never points at us. Uh, so uh, that is something to note. In actual data, this is how the pulses look. So these are two example X-ray binaries observed with the integral X-ray telescope, and the different panels actually show different energy bands. So you have the 20 to 30, 30 to 40, 40 to 50, 50 to, and so on in kilo electron volts. And what we see is even in different energy bands, the behavior of the pulsation is not the same. It's different, and this is because different phenomena are contributing at different energies uh, for the as far as the emission from these is concerned. Um, so a nice cartoon. This is actually from a nice PhD thesis that I've actually used for much of my talk from Ekaterina Sokolova-Lapa. This cartoon kind of summarizes what all different things are at play when we look at high mass X-ray binaries, what kind of emissions we get. So, for example, in the top left, we have energy dependent emission beaming. So, if you have different energies, you can get different beaming, you can get gravitational light bending. Uh, the geometry of the accretion streams also plays a big role on how the shape of the pulses is. Then you have the neutron star itself. The magnetic axis or the magnetic poles are not exactly always opposite to each other, right? They can be very complex, and that can also affect how different pulsars basically look different to one another. You also have this nice convective envelope around, or sometimes a disk, which can also reflect light coming from the neutron star accretion. So we also see signatures of that. I would also like to point out again that the pictures are not to scale. So these nice cylinders you see are of the order of tens of meters, I think, on the neutron star. But this is yeah. If we look at the spectrum, this is an example spectrum of Hercules X1, where we basically so on the x-axis we have the the energy, which is a proxy for wavelength or frequency. And on the y-axis we have the intensity. And what we see is the X-ray spectrum is not a very simple black body, right? It has many different components that are contributing, some stronger than others. But what we really see is we have the Bremsstrahlung radiation uh, acting. I think it's a dominant one here. Then you have the black body component, cyclotron. Cyclotron is can be a very useful diagnostic. So cyclotron is something that you need a magnetic field for. So if you don't see that, you could claim it. Well, if it's not there, that is consistent with a black hole. I'm not saying that proves that something is black hole, but if you see it, then it's most likely a neutron star. Um, but yeah, this is to give an idea of how the spectra can look in the X-rays. I will briefly go over the black hole case. We don't know actually all that many black hole X-ray binaries. We would like to know them, but there aren't just as many as we have neutron stars. So some key contrasting features that we have for these are that, well, there are no magnetic fields because we have the accretor is a black hole, and if there's no magnetic fields, we have no X-ray pulsations. Um, so black hole accretors will not show up as X-ray pulsars. This doesn't go the other way around. If we don't see X-ray pulsations, that doesn't mean it's not it's a black hole. You can also have, uh, like I said, some unfortunate alignment to the object, or it could be a quiescent state, or so on, that you don't see pulsations from a neutron star high mass X-ray binary. Black holes also have very characteristic spectral features that can separate black holes from neutron stars. It's not always easy, but in some cases, it really helps. Um, and again, to give an example of some X-ray spectra, in general, I think for high mass X-ray binaries with black hole accretors, there's two very popular states they can be found in. So there's a state called a soft slash high state or a hard slash low state. Uh, the names are a bit confusing, or at least I thought so. But the different states, you can also have an intermediate state. Uh, but the main um, driving factor for these states can be how material is being accreted onto the black hole, and how the disk around the black hole is behaving, and so on. So it is very common to see changes in such systems. So this, for example, is Cygnus X1, one of the most famous ones, but also very notoriously variable from time to time. if we go back to this plot and try to think their connection to binary black holes, what we see is um, for high mass X-ray binaries, sorry, for high mass X-ray binaries, uh, they still need to go through a lot more before they can merge. And some key aspects that need to be satisfied are they have to survive common envelope, the second star has to collapse into a black hole, and they have to merge within a Hubble time. So what we are seeing in LIGO Virgo Kagra uh, that we want to compare to high mass X-ray binaries, there's still a lot of uncertainty that separates them. A nice plot that kind of shows this. I'm sorry, this is a bit outdated. There's been a lot more black holes discovered in the meantime. But what we could already see back then was that the masses of the black holes in high mass X-ray binaries that we know and the ones that we've been founding in LIGO, there are a few that seem to be consistent, but we are finding more and more, much more massive black holes. So there have been new black holes that actually don't even fit in this plot. So of the order of 100 solar masses, and that I think raises a question of whether it's a metallicity effect or could there be multiple channels involved where not all high mass X-ray binaries are going to show up as the LIGO black holes that we see. Uh, Finally, I would like to quickly highlight uh, some interesting aspects of X-ray binaries and the scope for multi-messenger efforts. Because so far, what I've talked about is basically a tip of the iceberg. But if we look at the full picture, there are many ways to tackle such systems. So I didn't really talk about jets, but when you have accretion on these compact objects, you can also see jets. You can probe neutron star and black hole physics very nicely by studying how these objects interact with matter being accreted onto them. Of course, mass accretion is also a topic of its own. There have been efforts. I think I saw a nice optical interferometry paper, or at least a proceeding where they tried to resolve the winds of the system. There's radio interferometry. This I think is I think it deserves a lot more than one block in this slide because there's also extensive studies of high mass X-ray binaries in the radio wavelength. We can also use light curves in different again different wavelength regimes to understand how emission coming from different physical phenomena behaves throughout the orbit. On the theory side, there's evolutionary modeling. Could be 1D, could be 3D. There's a lot to be done there, but a lot of progress as well. Then we have detailed wind models, which are also, I think, ever improving. And finally, there's natal kicks, where since high mass X-ray binaries, by definition, uh, harbor a compact object, we can really understand how they have been, if they have been kicked, how they have been kicked during their formation by comparing to their host populations. Uh, so with that, I think I would like to end the talk here and leave my summary slide and take any questions.
Thank you very much, Kunal, for this fantastic talk. Um, Lecture, sorry. Do we have question in the audience? A lot of applause, as I can see. But questions? No questions.
Does that mean it was very good or very bad?
To me, it was very good, but and I'm sorry, I have no question. It's a bit too far from
Too
my
clear.
expertise, so I don't want to ask questions. No?
No, I think I would count it as good since I see people with background knowledge. So you cannot be that nobody else understood this. This is impossible given the audience. So I think it just shows that it has been clear.
Well, Then if no question, then
There's something in it. Oh,
yeah,
there's going
it's
to
a
be a
very
question.
good.
Thank you.
Well, then I suggest we thank you again, and we meet next week for the next lecture.
Yeah.
Thank you.
Thank
Thank
you.
you for the
Bye.
effort.